Hey, what's going on, guys? Let's look at this problem right here. Here this question is asking, sketch a body-centered cubic structure unit cell with a monoatomic basis. If the atomic density is 1.6 times 10 to the power of 22 centimeter minus 3, calculate the lattice constant. What is the atomic density per unit area on the 110 plane? What is the radius of each atom? What are the industrial and vacancies? Okay, let's see all of them. Now the first question is asking, sketch a body-centered cubic structure unit cell with a monoatomic basis. Now let's see how it's going to look like. So for a body-centered cubic structure, okay, so this is our cube. Okay, for a body-centered cubic structure, what we are going to have is, we are going to have a big like a full atom in the middle, and each corner we are going to have 1/8 of the atom. So each corner of this cube is going to have 1/8 of the atom, and one in the back, right? So there are 8 sides, we have 1/8 of the atom. So 1/8 times 8 side plus 1 atom in the middle, totally we have 2 atoms. Okay, now let's look at the second question. If the atomic density is 1.6 times 10 to the power of 22 centimeter minus 3, calculate the lattice constant. So when they ask for lattice constant, they are asking for this h length. Okay, now let's see how we can calculate. There's an equation we can use for this. This equation says density of the unit cell is equivalent to number of atoms in the unit cell divided by volume of the unit cell. Okay, now we already know number of atom in the unit cell, because for a body-centered cubic structure there are 2 atoms in the unit cell. So this is 2, and volume of density of the unit cell is given, that is 1.6 times 10 to the power of 22 centimeter minus 3, and the volume of the unit cell is going to be a cube, because volume of the unit cell, okay, this is going to be a cube because this is a cubic shape, and this lattice constant is going to be the length everywhere. Width, height, and the length is, all of them are going to be a. So since all of them are a, the volume is going to be a cube, so we can replace this one with a cube. So from this one we can find our a value, that is the lattice constant. That's the question is asking for, right? So let's go ahead and rearrange this one. So a cube is going to be 2 over 1.6 times 10 to the power of 22. Therefore we are going to have a is going to be cube root of, if you divide this one, you are going to get 1.25 times 10 to the power of minus 22, and that's going to be equivalent to 5 times 10 to the power of minus 8 centimeter. Okay, so this is going to be our a value. Now this is our a value. Now let's look at the second problem. What is the atomic density per unit area? So this is when we have unit volume, right? Now unit area, what we have to do is we have to divide this one by area. Now let's see how we can calculate area, and the plane is 110. Now let's get rid of this part. Okay, now let's see how 110 plane is going to look like. So here we have, let's draw this cube again. Here we have a cube. Let's say this is our z axis, this is our y axis, and this is our x axis. So when the Miller index is given 110, to draw the diagram, what we have to do is we have to take the inverse of this one. And if you take the inverse, you are going to get 1, 1, infinity, right? 1/0, that's going to be infinity. So infinity means it's this one never touches, or it touches all the points. So there are 2 possibilities. So the graph is going to, the plane is going to look like this. We are going to have 1 in the x, so this is 1. Since if it's infinity, it means it's parallel to z axis, so we are going to have something like this, parallel. and one in the y-axis parallel to z-axis, and the plane is going to look like this. It's parallel to z-axis. It never touches the z-axis, or it touches all the point. It touches all the point when you move this plane toward the origin, so it's going to touch all the z-axis. Now this is our plane, and we are interested in finding the atomic density unit area. We know there's the unit. First we have to calculate number of atoms. If you look at this one, each side of this H is connected with a cell, okay, I mean atom, and here you can see this 1/4 of the atom is covered by this plane, okay. So we can say 1/4 times 4, and for a body-centered cubic structure there's an atom in the middle, so it's also covered. So 1/4 times 4 plus 1, so that's going to give us 2 atoms. So here we have 2 atoms, and we had to find out the area in order to find the atomic density per unit area. Now to find the area, we know that since the lattice constant is A, this is A, and this side also A, and let's call this one L. L is going to be equivalent to A square plus L square is going to be plus A square plus A square using Pythagorean theorem. So L square is going to be 2A square. Therefore, L is going to be equivalent to square root of 2A. Okay. So this is going to be the hypotenuse. Now we have the hypotenuse, and since we know the hypotenuse, that's going to be the length of this one, right? Length of this plane, I mean, yeah, this plane, 110 plane. Length, we know the width is A, length is square root of 2A, so the area is going to be square root of 2A times the width, that is A. So we are going to have square root of 2A square, and if you calculate we already found out A, I forgot to note that down. That is A value we calculated, that is 5 times 10 to the power of minus 8 previously. So I'm applying that one right here. Square root of 2 times A square is going to be 5 times 10 to the power of minus 8 square, and if you calculate this area, you're going to get, okay, let's leave it as it is. Now we are interested in finding the densities, right? Density is going to be number of atoms divided by the area. Area is this one, square root of 2 times 5 times 10 to the power of minus 8 square. And if you simplify this one, you're going to get 5.65 times 10 to the power of 14 centimeter minus 2, right? This is centimeter square, so centimeter minus 2. So this is for the density per unit area. Now let's look at the next question. What is the radius of each atom? Okay, now let's get rid of all of this. Let's get rid of all of this thing and see how we can calculate the radius. Now let's look at the structure of the body-centered cubic structure. Again, I have to draw another cube. Okay, so here we have a cube, and for a body-centered cubic structure, as we mentioned before, each side have 1/8 of the atom. So here we have 1/8 of the atom, in the middle we have a full atom, and here also we have 1/8 of the atom in the corner. So from this corner to this corner, this is R, this radius. From here to here it's R. It's R, and since the radius is R, the diameter is going to be 2R, and this is also R. Okay, so 4R is the distance from here to here. And if you look at the bottom part from here to here, since this is A, this is also A, let's say this is L. If you use Pythagorean theorem, this L is going to be equivalent to A square plus A square. L square is going to be equal to A square plus A square, 2A square, and if you square root, that's going to be square root of 2A. So that's going to be equal to L. And L is going to be this one, square root of 2A, and this height is A, since this is a cube and equal length everywhere. So square root of 2A and this is L, this is A. It means we can calculate this distance 4r square, that is hypotenuse of this one. If you take this triangle, I'm talking about this triangle right here. So 4r square is equal to square root of 2a whole square plus a square, right? Plus a square. So from this one we can derive an equation for a. So this is going to be 16r square is equal to 2a square plus a square. Therefore r square is going to be 3a square divided by 16. Therefore we are going to have r is going to be equivalent to square root of 3a divided by 4. Okay, so this is the equation we are having for radius. Now square root of 3a divided 4 multiplied by a value previously we calculated, that is 5 times 10 to the power of minus 8 centimeter, and if you calculate this one, that's going to give you the radius, that is 2.17 times 10 to the power of minus 8 centimeter. So that's going to be the radius. Now let's see what are interstitials and vacancies. In crystals, normally occupied atoms in lattice points are not occupied, like in the corner it's not occupied. These unoccupied positions are called vacancies. Okay, and also due to spherical shape of the atom, when they are closely packed, a void is formed. This void side is called interstitials side. This void is filled by small size atoms, and these atoms are called interstitials, right? So those are the definition for interstitials and vacancies, and that's how we do this kind of problems. I hope this helps. Thanks for watching.